Nitrogen the Narcissist, presented by Quantum Agriculture. Nitrogen, the first electron-seeking element in the periodic table, is by far the most sensitive of all substances. As such, it is the basis of sensitivity, the carrier of intelligence, and its vehicle in the chemistry of consciousness. Were we to separate the nitrogen chemistry of our awareness from our carbon structure, this would be our awareness body, built up of amino acids, proteins, and DNA. In the 21st century, we are increasingly seeing the hypothesis tested that nitrogen is the vehicle of awareness and memory, along with its corollary that the human brain is a quantum computer. A growing understanding of quantum non-locality and entanglement, especially in regard to nitrogen, is closing the curtain on an era of institutionalized denial of telepathy, clairvoyance, astral travel, and prayer. Formerly, we have justified the denial of these realities with the lame excuse that we had no explanation for their existence, and therefore they cannot exist. That excuse no longer suffices. The question now is, how can we use this information? If we investigate a step further, the question of the form we obtain nitrogen in our diet, whether as crude industrial salts or as complex biological compounds, has an enormous, though as yet poorly recognized, influence on the clarity and integrity of our consciousness. The understanding of how to get complex biological nitrogen from the household of nature is a message of empowerment for those who want to take a hand in their families, and their society's personal self-development by growing food as though quality mattered, as though it was food for thought. Nitrogen is extremely versatile and reactive, forming strong bonds with many other substances, including itself. It forms the strongest bond in the periodic table with boron. In the atmosphere, nitrogen is completely transparent. It can only be seen when it reacts with other substances. In combination with hydrogen, carbon, oxygen, and sulfur, nitrogen is the basis of amino acid chemistry, proteins, and DNA. In the atmosphere, nitrogen is a colorless gas, completely involved with itself and unconcerned with its surroundings. By balancing the acidity of nitrogen, calcium makes nitrogen fixation possible. But it also takes a lot of energy to stir nitrogen out of its embrace with itself, which makes nitrogen fixation a very energy-intensive affair. Microbes take roughly 10 units of sugar to fix one amino acid. The same is true of industrial nitrogen fixation, which requires 10 units of methane to make 1 unit of ammonia. There are many nitrogen-fixing microbes in most soils. Legumes ensure they have enough calcium, but grasses are the best at supplying the required energy. Pastures are most productive when they have a balance of both grasses and legumes. Aside from DNA, chlorophyll is the most important protein in plants, whereas in animals this protein switches its magnesium for iron to become hemoglobin. A good source for both is stinging nettle, which is a high-protein plant and an herbal remedy for anemia. We see the mineral process of nitrate in the Chilean nitrate mines, which are a famous source of sodium nitrate along with various trace elements. Even though this has been used extensively as fertilizer, it is not the way we want to get nitrogen in plants. As anhydrous ammonia, a gaseous form of chemical nitrogen, we can seriously damage the biology and structure of soils. As urea, we do somewhat better, especially if we feed the urea to the soil biology using humic acid. Although plants have ways of converting nitrogen salts such as ammonium and nitrate into amino acids, it is best if the plants obtain their nitrogen in the amino acid form to begin with. This will occur if nitrogen fixation and protozoal digestion are occurring in the root zone of plants. The universal processes going on in amino acid nitrogen involve the widest expanses and the finest details of nature. Odors and flavors in foods are generally related to their nitrogen chemistry. Smells associated with breakdown of organic materials are an indication of nitrogen loss. Soluble nitrogen fertilization has done more damage than anything else in agriculture, with the possible exception of excessive cultivation. It shuts down nitrogen fixation, uses up soil organic matter, and grows weak, watery plants. Total testing may reveal large stores of nitrogen in the soil's humic reserves. Humified composts hold most of their nitrogen in insoluble forms, which are tied up in clay-humus complexes. Such composts will grow crops rather than weeds. Contrary to popular myth, maize is capable of feeding all the nitrogen fixation needed for good yields by the abundance of its root exudates. It is one of the most efficient photosynthesizers in the plant kingdom. Here we see where total nitrogen is 145 times as much as the soluble nitrogen, while the total phosphorus is more than 13 times as much. Potassium totals show a similar disparity between soluble and total analysis. Are NPK fertilizers the answer? Hardly. Since this soil is 5% organic matter, a large portion of this insoluble reserve is likely to be tied up in the soil's humus fraction in an insoluble but available condition. Access to the soil totals is the question and the answer rather than NPK fertilizers. Tissue tests are total acid digest tests of the plant's leaves or other tissues, another application of total testing. Taking leaf tests is important because it tells us what actually gets into the plant. All is not chemistry, as Liebig ended up realizing. Just because a soil has high levels of given soluble nutrient, say magnesium or calcium, does not mean this will get into its plants. The more soluble a nutrient is, the more it will crowd out other nutrients that are taken up by a plant. Thus nitrates, which are highly soluble, will block the uptake of amino acid nitrogen. Likewise, potassium, which is more soluble than calcium or magnesium, will block the uptake of both calcium and magnesium. Furthermore, nitrates are the antagonist of silica and impair its function in the plant, as well as shutting down nitrogen fixation in the soil, which is added reason to keep soluble nitrogen levels low so nitrogen fixation occurs, so protozoa can digest the nitrogen fixers and release amino acid nitrogen, which is very helpful for the growth of plants. And the plants can then take up these amino acids without stressing its transport system. Consuming extra sugars in the leaf to convert nitrates to amino acids, or freeing more energy to be given off in root exudation to feed further nitrogen fixation. Here is another example of a soil where soluble nitrogen is less than 5 parts per million, while total nitrogen is 2,579 parts per million. Even so, this soil is a bit hungry for nitrogen because it has a 13.24 carbon to nitrogen ratio, when ideally this should be 10 to 1 or less. Here we have a very light soil with a deficiency of organic matter and a 15 to 1 carbon to nitrogen ratio, which indicates it needs to build humic reserves and nitrogen fixing capacity. Although it would be common to mask its deficiencies of sulfur, boron, silicon, phosphorus, and zinc with nitrogen fertilizer, this would not build soil biology or soil fertility. Here is a leaf test from this soil which shows the effects of low fertility, which is not being remedied by the use of urea. One last analysis shows a heavy soil with a high pH, a TEC of 32, and a carbon to nitrogen ratio of 13.5 to 1, with low soluble nitrogen but good levels of most other nutrients, with the exception of silicon. It shows uptake of most nutrients, including nitrogen, but because of the high pH, sulfur and phosphorus are not taken up well. Though the leaf test shows low nitrates because of the high pH, the plant has taken up more ammonium than is desirable. Also, high uptake of potassium seems to have blocked the uptake of calcium. Here we see the effect of no nitrogen fertilizer on a portion of this potato crop. In this picture, we see the effect of no nitrogen fertilizer on this certified biodynamic potato crop. Here we see plots of maize given different rates of nitrogen fertilizers. The intent of this trial was to show the need for nitrogen fertilizers, all else being equal. However, levels of other nutrients and the soil biology were not considered. The deficiency symptoms in this picture were also attributed to lack of nitrogen, though more probably it was sulfur and potassium deficiency. Here we see maize grown with no nitrogen fertilizer on healthy biological soil on a certified organic farm. Synthetic nitrogen fertilizers make plants dependent on them. They are addictive. If one uses synthetic nitrogen, then one will need to keep using it, even though the benefits diminish. Whatever the source of nitrogen, it should always be complexed with humic acids, either by composting or mixing with humates and fed to the mycorrhizal fungi in the soil. All sorts of plants feed nitrogen-fixing bacteria. Maize interplanted with soybeans, dairy pastures, and herbs such as stinging nettles. Animal wastes need composting or complexing with humates before adding them to soils. This will avoid weedy growth and will not impair biological nitrogen-fixing processes. Homeopathic remedies are economical and an easy method of applying biodynamic patterns related to the various plant and animal processes that work together in the ecology of nature to balance and support life. Always pattern inputs, whatever they might be, fertilizers, fertigation, foliar sprays, because this activates the inputs.